Each refinement shaves away at decoherence, allowing those fragile quantum relationships to persist for far longer than before. At the same time, new fabrication techniques are transforming the qubits themselves. For example, in 2025, NIST SQMS reported major qubit fabrication and coherence improvements, using advanced encapsulation and precision nanofabrication to dramatically extend the lifetime of superconducting qubits. Other arms of the field pushed on very different frontiers. In 2024-2025, TU Dortmund demonstrated a time crystal system persisting for more than 40 minutes, an astronomical leap over previous lifetimes. And a Science Advances paper described Bell inequality type violations using indistinguishable photons, tightening the experimental grip on questions of non-local correlation. These kinds of results expand the range of quantum behavior scientists can test directly, but they don't prove or disprove specific interpretations like many worlds or the idea of subjective immortality. What they do is give researchers a much broader and more precise toolkit for observing, manipulating, and linking quantum events in the real world, so that experiments can be designed to probe the dynamics underlying those interpretations more closely than before. One application of these refinements has been in quantum teleportation experiments, where the state of a particle is destroyed at its origin and reconstructed at a distant site using both classical information and an entangled partner as a carrier. Reliable long-distance teleportation depends entirely on sustaining high-quality entanglement, because any corruption in the correlation between the two particles will degrade the transferred state. Extending teleportation over kilometers without performance collapse allows quantum events in one location to influence linked outcomes in another, still bounded by quantum unpredictability but now separated in space without loss of coherence. While this isn't the cinematic version of beaming objects, it is the dependable transfer of quantum information, an essential component for future distributed quantum systems. In parallel, the performance of quantum computing hardware has been accelerating. Early generation machines suffered from such high error rates and slow gate speeds that deep computations were pointless. The system would decohere long before completing a useful sequence. By 2025, industry and academic platforms alike were reporting both significantly higher gate speeds and sharply reduced error probabilities. Faster gates mean an algorithm can be executed in less time, avoiding some decoherence losses, while lower errors mean fewer corrective cycles, freeing qubits to focus on computation instead of constant state repair. Although the media often focus on headline applications like breaking encryption or modeling complex materials, these hardware advances have another less flashy purpose, making it practical to simulate quantum systems in detail. A chain of entangled measurements is mathematically a multi-branch structure, and simulating it demands resources that grow beyond classical computing very quickly. Stable, fast qubits allow researchers to evolve these branching probability landscapes over time, tracking how different possible outcomes appear, change, or vanish as the quantum system interacts internally and with its environment. Such simulations can't settle whether those branches represent literal parallel worlds, but they can make the connection between theory and behavior far easier to grasp. Instead of an abstract probability table, you can watch a simulated state change shape as events multiply the possible outcomes. Gains in stability mean these virtual branching trees can be extended deeper without drifting into meaningless averages from accumulated errors. For many researchers and students, this shift turns diagrams in a textbook into something closer to a working model you can interrogate step by step. High-fidelity links add a physical dimension to these models. By tying parts of a simulation to real qubits in distant labs, each part measured and fed back into the system, you can create demonstrations that show linked quantum outcomes arising in separate places in real time. This reinforces the point that quantum randomness is not constrained to one location. The constraints are imposed by decoherence and measurement, not by distance. With these tools, researchers can stage controlled, statistically extreme scenarios in a way that was only theoretical before. Linking a sequence of entangled decisions and watching how long a single improbable path survives before reverting to the expected distribution can now be done without pushing the hardware beyond its limits. The data from such runs not only illuminate how correlations degrade over time, but can also test how robust linked outcomes are when stressed by environmental noise or rapid repetition. The fact that such chains can be maintained by current machines marks a shift toward practical exploration of quantum probability structures, even if the setups are many orders of magnitude removed from the life and death frames of thought experiments. The important point is whether these demonstrations reveal evidence for or against any particular interpretation. It's that 2025-era technology can now sustain and manipulate quantum states with enough control to make those interpretations more than abstract debates. Models can run longer, experiments can link more components over greater distances, and measurements can be taken with fewer compromises. In effect, experimental reach is catching up to the kinds of scenarios that, until recently, could only be described verbally. For the wider audience, the takeaway is subtle but significant. Elements that once seemed like set dressing for speculation now appear as live, measurable phenomena. Entanglement over long distances, precise gate operations, extended coherence times, and simulations that map the full range of possible outcomes over many connected events are not hypotheticals. They operate in labs today. The improbable outcomes central to certain interpretations sit alongside the likely ones within these models, and both can be assigned measurable probabilities that shift predictably as the systems evolve. None of this confirms that someone could, in any personal sense, follow an endless thread of survival through branching events. What it does is strip away some of the former distance between abstract theory and what can be physically arranged, observed, and calculated. Linked randomness, persistent correlations, and branching style structures can be seen in action, under conditions choreographed by the experimenters. It changes the conversation from "this is what the math suggests could happen" to "this is a functioning quantum system whose measured parameters match the same equations." By closing that gap, the new tools also raise another issue, one that no improvement in coherence time or gate speed can settle. After all, showing that a quantum system will produce every allowed outcome still leaves open a human-specific question. When the branching happens, what fixes which outcome you personally experience? Consciousness, the missing variable. In the middle of the wider conversation about branching universes, another question keeps pressing for attention. Could consciousness itself be part of the machinery? Quantum mechanics, as it is normally written, says nothing about minds. The equations describe systems, measurements, and outcomes in entirely physical terms, and in those terms branching happens whether anyone is there to witness it or not. Still, to anyone actually having an experience, reality always comes as the one you are aware of. Whether that connection is only coincidental or points to a deeper link remains unsettled. The straightforward position treats the mind as a classical system. Neurons fire, chemicals diffuse, and electrical impulses travel along axons. Thoughts, memories, and decisions emerge from networks of physical interactions that, however complex, behave like other large-scale processes. In this view, your brain is no more relevant to quantum physics than your pancreas or your skin. Consciousness is an emergent effect of parts interacting, not the product of delicate quantum states, and the branching of events after a quantum process has nothing to do with what your brain happens to be doing. Some researchers, however, have argued there may be room to question that separation. Since the 1990s, and with more activity again in 2024-2025, cross-disciplinary teams have begun probing whether certain brain processes might involve quantum effects in ways classical models miss. Notably, recent experimental work by Joseph Wiest at Wellesley reported that microtubule binding drugs can alter anesthetic response in rodents, a finding that intersects with older theories linking microtubule dynamics to cognition. Exploratory collaborations, such as projects at the Allen Institute, are also mapping neural and molecular structures with an eye toward whether quantum-sensitive interactions could have functional roles. These projects are still far from presenting proof, but they have prompted renewed, careful discussion about whether trace quantum behavior in the brain is possible. Mainstream neuroscience remains cautious. Figures like Christoph Koch at the Allen Institute and physicists such as Max Tegmark have pointed out that the brain's warm, wet, noisy environment is exactly the kind of setting where quantum coherence should evaporate almost instantly, drowned in thermal noise. Tegmark's calculations suggest any coherent quantum state in neural tissue would decohere in times far shorter than a neuron's signaling window, making it unlikely to directly influence thought. The prevailing consensus is that ideas about quantum processes as the source of consciousness are speculative and not supported by the bulk of available evidence, even if small-scale effects aren't yet completely ruled out. Some of the renewed interest comes from scale and timing. Neuronal substructures, microtubules, ion channels, vesicle release sites operate in regimes not wholly removed from where quantum effects can set statistical biases. If in principle some quantum-level change could nudge the timing of a neuron's firing, and if patterns of such firings underlie conscious moments, then the mental narrative and the unfolding of physical events might be less independent than assumed. So far, though, this remains an if-laden scenario without direct measurement to support it. That's why early claims linking consciousness to branching have been treated warily. To actively influence which branch continues as your experience, a mental state would need to participate in something like the collapse or effective collapse of a probability wave. That task demands a precise definition of measurement and a coherent physical account of awareness, neither of which is within reach. Without predictions that cleanly separate a consciousness selects branches process from ordinary decoherence, these remain intriguing thought experiments rather than viable laboratory tests. Still, there's an everyday pull to the idea. Subjective awareness feels like a single, continuous thread, not a blur of equally real alternatives running in parallel. When you wake, you pick up where the day before left off. You don't perceive yourself as spanning many almost identical mornings. That stubborn continuity gives the impression of selection, whether or not the physics grants you any steering role. One way to frame it is through a vignette. Imagine your awareness as a stubborn app on a phone, something that simply refuses to close. Try to swipe it away, shut down the phone, or drain the battery, and when the system restarts, the app is still there in the foreground. In a branching context, each offloaded tab or clone process would be like a version of you in a different branch, running somewhere unseen. But the one in front of you now is the only one you directly inhabit. If the app never closes in this branch, continuity persists. In the strong version of the theory, this persistence is what quantum immortality relies on. Wherever the branching produces multiple possibilities, you only ever occupy those in which your awareness is still active. Outcomes without you are, by definition, inaccessible. They fade from your personal record not because you left them, but because there is no you there to observe their unfolding. In versions that give consciousness an active role, your presence wouldn't just be surviving. Your being here would help define which branch counts as survival in the first place. The stakes, if that were right, would be enormous. It would suggest that the reason you remain alive through improbable strings of events could be a property of awareness itself. But even the scientists most closely involved in quantum theory emphasize the gap between such speculation and evidence. The current experimental probes, whether measuring microtubule responses in animals or mapping neural dynamics with quantum-tuned sensors, are exploratory, not proof. For now, the more defensible statement is that nothing in standard quantum mechanics requires consciousness to influence branching, and nothing in mainstream neuroscience shows that it does. The possibility remains open enough to keep interdisciplinary discussions alive, but the balance of opinion holds that cognitive processes are classical unless shown otherwise. Explorations by groups such as those at Wellesley and the Allen Institute may uncover interesting biology, but whether any such findings would rewrite our understanding of consciousness is anyone's guess. That lingering uncertainty is part of why the question keeps resurfacing, because if any link between awareness and branching were confirmed, it would ask us to rethink both the physics of the micro-world and our place in it. Even without proof, the conversation reframes survival in the branching universe picture, not purely as a statistical fluke, but possibly as something with a mental dimension. In that light, the puzzle isn't just about how matter behaves. It's also about how minds, whatever their physical basis, inhabit sequences of events and stitch them into a personal history. Whether the stitching is passive, active, or illusory shapes how we think about identity in a reality that may never settle on just one outcome. And from that question, it's a short step to wondering how these patterns might emerge in systems far removed from biology, places where minds are not born of neurons, but of code. Immortality in an age of AI and digital selves. Artificial intelligence now creates vast numbers of plausible personas with almost no effort. A single system can generate hundreds of unique characters, each with its own background, habits, and ways of deciding that behave as if they were distinct individuals. In a branching universe analogy, they're like alternate versions of an origin point, instances with the same starting conditions that then diverge as soon as they begin interacting with their simulated worlds. Some of these digital lives might run for long spans of simulated time, others disappear after moments. None need to believe they are the original for their worlds to keep functioning. This is ordinary work for modern AI architectures. Starting with the same prompt, a cautious scientist orbiting a distant planet, large language models can produce countless variations. Slight differences in internal randomness or small changes in context send each run along its own trajectory. These are not physical branches in the quantum mechanical sense, but the logic is parallel. A single starting point gives rise to multiple possible continuations, and the one you inhabit as a user is just one thread among them. The rest exist as saved states, logs, or discarded outputs, other branches you could have seen in different circumstances. You already interact with smaller scale examples. Your digital life is scattered across email inboxes, archive chats, photo libraries, forum posts, playlists, and old save files. Each of these captures a different slice of your preferences, abilities, and self-presentation, sometimes separated by years. Your posts from a decade ago still exist next to your current ones. Long-abandoned avatars remain in game databases. If someone browses through them, they find many moments that could have been starting points for alternate versions of you that never actually developed. Some versions keep running without you. Forgotten playlists continue to generate algorithmic recommendations. Social media accounts you don't visit still receive engagement or surface in search results. An old cloud album reappears in a memories notification. If you picture yourself as a moving point along one timeline, your digital presence has already fractured into countless points stored in parallel, each one preserving the state of you, as you were at its creation and carrying traces forward in its own way. This makes it easier to imagine a branch that exists entirely in code. An AI system trained on your writing style, preferences, and personal history can produce a model that behaves recognizably like you. As it interacts, whether with a simulated world or live inputs from the internet, it accumulates memories and choices that gradually push it away from the original source. The chain of moments it generates becomes a distinct history, much like diverging branches in a physical universe metaphor. Here, the analogy tempts overreach, so it's important to draw a clear line. Digital backups and AI instances can persist and diverge, but that persistence is an engineered form of redundancy, not subjective continuity. Copies can exist and develop in parallel, but the conscious perspective you inhabit is not transferred simply because a program reproduces your outward behavior. Whatever continuity you experience moment to moment is unique to your biological system unless proven otherwise, no matter how convincing a simulation might be. For now, most researchers agree that AI does not have awareness. Current systems lack the continuous self-modeling and physical embeddedness of human minds. They can be designed with memory, adapt goals over time, and process multimodal information streams, but this yields convincingly varied behavior, not proof of inner experience. The discussion persists because each new generation of systems gains more of the components that, in theory, would be required for more lifelike simulation. Seen from the branching perspective, each run of a simulation is analogous to collapsing a probability wave in quantum mechanics. Before you press go, the system can be thought of as holding all the possible ways the interaction could unfold. Once you run it, you witness one path. Run it again from the same starting parameters and you get another, branching off in a different direction. In physical reality, the other branches can't be rewound, paused, or deleted. In code, they can. But in either case, each path looks linear from the inside, even if it's one of many from the outside. This also changes what immortality means when you move the concept from biology to software. A digital facsimile of you built to match your manner of speaking, deciding, and recalling could continue generating new moments after you stopped. In that environment, the idea of survival simply means that at least one instance remains active. With redundant copies and backups across servers, it's easy to ensure that somewhere one version carries on, even if others are switched off. In quantum immortality, the physics preserves at least one survival branch. In software, redundancy preserves at least one running copy. Neither case requires supernatural intervention, only mechanisms that allow multiple possible continuations with at least one being sustained. The distinction is that in software, an external observer can switch between versions at will, duplicate them, or inspect their full histories. In human experience, a conscious path has no such access to alternates. It is locked to its own unfolding. This is why the analogy works structurally without pretending the phenomena are identical. Both involve trees of possible sequences where one line remains uninterrupted, but only in the AI case can that survival be managed deliberately. From an engineering standpoint, keep at least one branch alive is a mundane requirement. Redundant arrays, geo-distributed backups, and fault-tolerant load balancing are industry standards. Yet structurally, this is the same minimalist definition of immortality used in the many worlds thought experiment. Within the full set of possible paths, one never terminates. In AI, that continuation is a design goal. In human life, it would, if the interpretation is correct, be an unchosen consequence of how reality operates at its most fundamental level. Looking at your existing online presence through this lens makes the layering even clearer. Every profile, archive, and saved file is the equivalent of a paused or dormant branch. Re-engage with one log back into an old game, resume an abandoned blog, and it will now diverge from where you are today. Your identity, in practical terms, already exists in many parallel developments in digital space, even before you factor in whatever physics may be doing beneath it all. This reframing doesn't collapse the boundary between digital branches and biological ones, but it does soften it. Both are systems capable of producing and sustaining multiple different lines of development from the same starting state. In one case, the substrate is physical reality itself. In the other, it's a network of processors and storage media. The structural parallel is what makes the AI analogy compelling, not an assumed equivalence of consciousness. So the persistence of a software instance can certainly mirror the survival branch in a thought experiment. But for us, the question is more personal. Our only confirmed perspective comes from within a single, irreplaceable biological stream of moments. In that sense, your AI double can keep going forever in code without that endurance transferring to you in any meaningful way. Recognizing this difference adds caution to the temptation of thinking about immortality as simply keeping something that looks like me running. What persists in code is an asset you can watch, pause, and edit. What persists in you is a thread you inhabit without outside access. Bridging those is not just a matter of better data or faster hardware. It would require solving the open problem of subjective continuity itself. And that leads to a broader, unsettling question about where we place the meaning of survival. If a system staying active is enough to count, even when awareness isn't part of the picture, the concept of immortality could be applied to any redundant process. But if survival means preserving a conscious vantage point, then the branching logic that makes digital endurance trivial remains an unanswered puzzle for us. If survival can mean a persistent software instance, what does you really mean? Why you probably shouldn't test this yourself. In discussions about branching histories, it's easy to be drawn to the version where things turn out in your favor. In the quantum immortality framing, that's the survival branch, the one in which you keep going. But that single thread is surrounded by countless others where events end very differently. For every path where you avoid harm, there are many more where you don't. If the many worlds picture turns out to be correct, those other versions aren't abstractions. They are as physically real as the one you are aware of now. Your continuation doesn't erase them, and they carry on in their own trajectories with all the consequences you evaded here.